Okay, awesome. Looks like we've started. Hello, welcome back, everybody. Today we're going to be talking about verifying trig identities. So when you're looking at your trig identities, I just kind of rewrote the basic ones that we're going to look over today up top. So we have our reciprocal identities, our quotient identities, our Pythagorean identities, and we also have our co-function and even odd identities. We'll use those a little bit less. But when we're verifying them, we'll be using these different identities in equations to solve for our left and right-hand sides of our equation. So let's get right into it. If you need to pause and look over these identities real quick, I implore you to do so. So first, we're going to start off with the fact that we are working with our left-hand side and our right-hand side of our equations independently. So this is something kind of new, right? Normally when we look at our equations, we use both sides together. You know, if I have x plus 2 is equal to 5, well, I subtract 2 from both sides. I'm subtracting it from both the left and the right to get my final answer. But here we're not going to do something like that. It's going to be much more working with one side to find if it's going to be equal to the other side. So we're going to have some guidelines to work on this. So an important thing to remember is just LHS means left-hand side, RHS means right-hand side. That's just kind of a vocab thing. You always need reasons to move forward. So just like when you're doing geometric proofs, back in the day, you guys had to say, you know, you have to have a reason for why you're taking the next step. And the reasons we're going to often have here are our identities. We're going to use some algebra tricks. So, you know, remembering things like factoring, remembering your common denominators, remembering how to get a monomial denominator, those things are going to be really useful. And last but not least, we're obviously going to use our fundamental identities that we talked about in our last class and kind of throughout our last unit to break these down. So I think the best way to get into these is examples, because we can just look at the trig identities all day, but until we actually start verifying them in practice, I think it's a little hard to see. Let's look at one example, and this is in your textbook, so if you need to reference it on the Canvas resources page, you can. So let's start with secant squared of x minus 1 all over secant squared of x, and that's going to be equal to sine squared of x. And so we have our left-hand side and our right-hand side. Another important thing is going to be to start on the side that looks more complicated, right? I have sine squared x on the right-hand side. And I mean, I could rewrite that as 1 over cosine or cosecant squared x, but that's probably not going to get me anywhere. I might go a little bit in circles. But the left-hand side of this equation, it looks a little bit more complicated. So I can probably simplify it down to sine squared x. So we're going to start off with that. And I'm going to write down the reasons why I'm simplifying at each point in this one. But as we go further on, I might start skipping over that. So let's start off with just the right-hand side rewritten. And talk about what's the first thing we're going to do. So I think the first thing I'm going to do is use the Pythagorean identity that 1 plus tangent squared x is equal to secant squared x. And I'm going to replace the secant squared x in my numerator with that. And this is because now we have a plus 1 and a minus 1, so I can kind of simplify the equation using that. So if I put a reason over here, I would use my Pythagorean identity. From here, we can start simplifying. So we'll just have tangent squared x over secant squared x. And the reasoning for that is just that we're simplifying. And from here, I can kind of think about my reciprocal identity. So we can make this equal to tangent squared x. 1 over secant squared x is going to be the same as cosine squared x. And then from here, I'm going to use my quotient identity. So I remember that tangent squared of x has to be the same as sine squared of x over cosine squared of x, all times cosine squared of x. And now we can cancel these two cosine squareds out. and we'll get that our final answer is equal to sine squared of x. And that is the answer we wanted. We wanted to verify that that original function equaled the right-hand side, which was sine squared of x. So when you solve these equations, you're just kind of going through and trying to get the two sides to match. Normally, you only need to look at one side to do this. Sometimes you might need to work with both, but you have to remember to keep them independent. We didn't use any part of the right-hand side to do this. We just kind of remembered what was our goal, what were we working towards. So we're just going to use different versions of these identities to kind of work through these problems. And I'll do a couple more examples to show you basically the different ways you'll use these identities. And there's more than one way to use identities in a problem as well. So that problem we just did, secant squared theta minus 1 over secant squared theta is equal to sine squared theta. There's actually a shorter way to do it. I could just rewrite this fraction as secant squared theta over secant squared theta minus 1 over secant squared theta. Nothing wrong with that. I'm just rewriting a fraction. It's still algebraically the same. And then we can simplify this. Secant squared theta over secant squared theta is just 1. And 1 over secant squared theta gives us cosine squared theta. Oh, sorry, I'm switching between thetas and x's. That's bad notation on my part. And then this just simplifies to sine squared theta based on the Pythagorean identity. So what's really nice about this is, these problems can be approached a bunch of different ways. So you just kind of have to take a crack at it in whatever way you think is best. So let's look at another example in its entirety. So in this example, I have 1 over 1 minus sine of alpha plus 1 over 1 plus sine of alpha is equal to 2 secant squared alpha. Here, alpha is just another Greek letter. It's just like x or theta or u, just another variable. So the first thing I'm going to start off with is I don't like having these two separate terms in different denominators. So I'm going to start off by kind of combining everything on the left-hand side. So I'm going to have to multiply my first term by 1 plus sine alpha. I'm going to have to multiply my second term by 1 minus sine alpha. And then my denominator is going to just be 1 minus sine alpha times 1 plus sine alpha. Again, I took the more complicated side just to kind of make it a little bit easier for myself. From here, I can kind of simplify. I see that sine of alpha in the top are going to cancel out, and I can group 2 together. So I'll have 2. In my numerator, I can FOIL. So we'll get 1 squared, which is 1. Our inner terms are going to cancel out because we have a plus and a minus. So we'll just get 1 minus sine squared alpha. And we can rewrite that as 2 over cosine squared alpha using our Pythagorean identity. And from there, we can use our quotient identity and we get 2 secant squared alpha, which is equal to the right-hand side that we originally started with. And so we're done from there. So it's always important to kind of get things in the most algebraically simple form you can, if that's the goal. I'm going to show you a couple more examples. So let's do example number 3. So here we have tangent squared x plus 1 times cosine squared x minus 1 equals minus tangent squared x. So first, we want to identify, should I solve for the right-hand side or the left-hand side? Here, the left-hand side is a lot more complicated, so I'm going to go for that one. That's the one I kind of want to simplify. And I think this is one where it's pretty clear we know where we should start. So we have tangent squared x plus 1. That's a Pythagorean identity. So we can rewrite that as secant squared x. And then from there, cosine squared x minus 1. It does give us information about a Pythagorean identity. It's just not in the most standard form. It's going to be minus sine squared x. From here, it's actually going to be pretty straightforward. We can use the fact that we have minus sine squared x, use our quotient identity to get this into, or our reciprocal identity, sorry, to get cosine squared x in the denominator. And from there, we'll use our quotient identity because we know sine over cosine is tangent. So sine squared over cosine squared is tangent squared. And we'll have tangent squared of x. And that is going to equal our right-hand side. There's a couple more examples like this in the book, but I'm just going to go through two more that kind of show a couple more techniques that we'll use, just so we kind of get a full flavor for all of these. But the idea is always to kind of just, start with, let me take the most complicated thing, let me kind of work with it, let me see where I can get using my identities. So this example, I want to pay particular attention to, because in this one, we have to work with both the left and the right-hand side. So let's look over this. So we have cotangent squared theta and 1 plus cosecant theta is equal to 1 minus sine theta over sine of theta. And again, I want to emphasize, you might start these problems off differently than me. I might pick the left-hand side, you might pick the right-hand side for problems where both sides are kind of equally complicated. But at the end, you should get two things that equal each other based on looking at the left and right-hand sides independently, not using them with one another. So here, for example, I want to be able to multiply both sides by sine theta to cancel it out on the right-hand side. That's not something we use in proofs. We want to work with them independently. And if it helps, you can always kind of draw a dotted line going down to kind of separate them out. So I'm going to start off with the left-hand side. So I'm going to simplify this with factoring. So we're going to take first the fact that we know cotangent squared theta is equal to cosecant squared theta minus 1. So we've rewritten that. And now that we have that, we can factor, because this is kind of a, 1 minus a squared situation. We can factor that to 1 plus a times 1 minus a. And so here we can have cosecant squared theta plus 1, not cosecant squared theta, just cosecant squared, just cosecant, theta minus 1. And divide by 1 plus cosecant theta. We see that we have a common term here, cosecant theta plus 1, 1 plus cosecant theta, those are the same thing, so I can just cancel those out. And I'm left with cosecant theta minus 1. Well, from here, this doesn't really look like my other side. So there's two things we can do. I can keep going on the left-hand side, or I can try working with my right-hand side. So let's start working on our right-hand side, and I'll show you another way we can do it later. So with our right-hand side, let me just write that we've kept it the same so far. So it's been 1 minus sine theta over sine theta, 1 minus sine theta over sine theta, and so on. So we could take this side, our right-hand side, and end up splitting the fraction. So we have 1 over sine theta minus sine theta over sine theta. And that's going to give us cosecant theta minus 1. And that gives us the same thing as this left-hand side. So it's okay to use both sides, but again, I didn't go back and forth between the two sides. And I could have also done this just staying on the left-hand side. So I could have said that this is the same as 1 over sine theta minus 1, and then combine the fraction. So I would have 1 minus sine theta over sine theta, and got my original answer without ever having to use the right-hand side. So do whatever you're most comfortable with, but just remember that you're keeping those independent. The last example I'm going to do kind of refers to expanding what we're working with. And this is actually really, really useful for when you guys go into calculus. Particularly in Calc 2, you'll be working with trig identities in your functions. And these identities are really useful there. So let's look at this as example 5. So this will be the last one we'll do, and I'll let you guys go. So let's say we start with tangent to the fourth of x, and we want to verify that it equals tangent squared of x secant squared of x minus tangent squared of x. So remember, I said this is an expansion problem. So even though the right-hand side is more complicated, we're actually going to start with the left-hand side and try to get to what we have on the right. So taking tangent to the fourth of x, we don't have any identities that have things going to the fourth power, but we do have identities going to the second power. So the first thing I'm going to do is just factor this to be tangent squared x, tangent squared x. And from here, I can use my Pythagorean identity because tangent squared x is going to be the same thing as secant squared x minus 1. Multiply that by tangent squared x. And then from there, we just distribute. So we'll have tangent squared x, secant squared x, minus tangent squared x. And this is going to be equal to our right-hand side. So here, these might seem kind of counterintuitive because you're like, well, why are we taking it from the simplest form and expanding it out? But in calculus, this ends up being really useful for solving things because we tend to just solve things best at the squared level for our different trig functions. So you have something larger than a second value. So if you have something higher than a squared value, if it's cubed or to the fourth power or to the fifth power, that's going to tell you that you need to expand it and that you're going to have to get a form out of it in that way. So that's going to be the one case in which you start with something that looks really simple and expand it out. But for the most part, if you have something with lower powers where it's just raised to the 1 or 2, you're going to be working with just the most complicated side. And that's all the examples I have for now. I hope this helped you guys understand kind of how we use our trig identities in verifying them, how we go about these proofs. And I hope you have a great day. Thanks so much for watching. If you have any questions, let me know. If you were confused, go back and slow it down. If this was easy, I hope you breezed right through it at 1.5 speed. Have a great day. Bye.